这个可以放，这个可以放，把它收起。
哦，好啊，等下这边我把它点下去。
这方面可以收起。
现在这样应该是开始了。
对。
那就这样。
但是你看不到了。你要
没有关系，要 switch 再 switch。
哦 ，OK。
现在应该是开始了。
开始了。
嗯。
OK。
我来问一个。
这个开了没有？
还没。
好像够。Okay. Let us begin our class today. Today I'm going to talk about the response of dynamic systems. Because we know that when you solve an ODE, then you get solutions. Then how do you characterize the solutions? So how can you quantify the solution? That's the subject of this lecture today. So that's what I call response of dynamic system. The outline, I will talk about the single degree of freedom first, then then 2 degree of freedom. Then I continue to talk about multiple degrees of freedoms. And however, that the bending vibration of beams, I may not have time to do it, and I may not do it. I may not talk about that subject. Okay, let's talk about the first order system. Now, this is the simplest dynamic system you can ever have. So we have dw over dt plus aw equal to a small a, and then a larger A cosine omega t. The reason why I have small a here and then I have capital A here is just the show you the solution. I can simplify the solutions, and that solution looks very pretty. Okay, so the A, small a, and larger A, they doesn't make any physical sense. That's just for my mathematical convenience. So you may think about the small a and larger A, multiply them together as a one constant. And you will see why I want to do that later. So the small a there, that belongs to the system A. The larger A here, that really belongs to your input force. So they do represent two different constants in two different sides. One is on the left hand side, that's the system side. One on the right hand side, that's your input side. Okay, now let us look at this. That's the approach I also showed you last week. Now I define a new operator. I call that the operator the d square over dt square plus omega square parentheses. I call that a new operator. The reason why I define that operator because my force input is cosine omega t. Okay, now for that new operator, we know that. Let me show you that new operator. I think I already showed you last week. That new operator, when you operate the right hand side of the equations, then that will be 0. So that's why I introduced that. So that's new operator dt square plus omega square when we operate the right hand side of the equations, that equals to 0.
应该换过。
Yeah, so the new operator, if you look at new operator, if you look at that, the new operator operates the right hand side of the equation that equal to 0. Okay, so if I operate both sides of the equations, I operate on the right hand side becomes 0, but operate on the left hand side, then if you can see that that is, so you switch already down?
Okay, I had switch again.
You switch, yeah. Okay, so so this is how so if I operate both sides, this is operate on the right hand side, you operate on the left hand side, and that's in my slides. So okay, now you can switch back. Then when I operate on the left hand side, then we'll get then I get the this equations. That means t squared over dt squared plus omega squared parentheses that left hand side of the equations. Then I got that that equation. Then I have the t squared over dt squared plus omega squared and parentheses, and then parentheses d over dt plus a. That a is your system A. Then parentheses w equals 0. That produce the solutions I call characteristics equations, and that produce lambda square plus omega square, then parentheses lambda plus a, parentheses equal to 0, and that gives you 3 roots, or you call eigenvalues. The 3 roots, lambda equal to plus or minus I, and then lambda equal to minus a. Okay, let me ask you one simple question. Which lambda belongs to the homogeneous solutions? So any equation like that, we have 2 parts. One is homogeneous solution, one is particular solutions. Or I call one is a transient response, one is a steady state response. Now I have 3 lambda there. Now which lambda belong to the transient response, and which lambda belong to the particular solution called steady state solutions? Any idea? We have 3 roots. Huh?
Plus or minus I.
Plus or minus I belongs to what? Homogeneous?
Yeah.
Or particular solution or homogeneous? Are you sure? Homogeneous solutions? Well, for first order equations, how many roots is supposed to have? 1. If I don't have forcing functions, forget about forcing functions, okay, cosine. So which one is the homogeneous solutions? Minus a, right? Okay. So we have 3 roots. One is minus a, one is plus minus I. So obviously that's minus a is from the system, as if from the system itself. Minus a. Plus or minus I is from the cosine omega t. That's from your forcing function. So we have a solution like this. Solution is Wt equal to C E exponential lambda at plus C1 cosine omega t, C1 sine omega t plus C2 cosine omega t, right? And that's solution. Am I correct? No, you forget about your engineering mathematics already? Your ODE? The solution is right? Okay. Now, how can I solve C? There's a C and C1, C2. How can I solve C? You must know what? Initial conditions. How can I solve C1 and C2? How can I solve C1 and C2? I'm going to solve C1 and C2. It's very simple. Sub that solution into your original equations, you will get C1 and C2. So a substitution of that solution into the first order system equations, then from that, the homogeneous equation that's involved A that will be gone because that's a homogeneous C. The C will be gone because that's homogeneous solution, right? So you get C1 and C2. So you sub that equation in that solution into the first order equation, then you got C1 and C2. Agree? C1, C2 does not, C1 and C2 do not depend on initial condition at all. It depends on your input. That's a particular solutions. That's come from particular solution. You follow me or you don't? Are we in peace? Right? Keep you locking. Well, that's the question you might have the answer in my midterm, right? Not your midterm, not mine. So if I sub these equations, if I sub these solutions, if I sub these solutions into that equations, then that's how I got C1 and C2. Oh, okay, agree? Any problem? No? Okay. So I got a C1 and C2 solved. Now C1 and C2 will be function of capital A, small a, and omega. That's omega is from particular solutions. So I have the frequencies of input, that's omega in there. I have the capital A, that's related to the amplitude of your input forcing functions. That's A, larger A, cosine omega t. I explained to you already that that A, small a, and larger A, I put there just for the convenience. And so I add a small a on the right hand side. So you just consider small a multiplied by a larger a, that's just a constant, all right? Okay, now we got this. Now, the solution here, I'm not teaching how you solve the equations. My job here is explain to you the physical significance of that solutions. All right, I'm going to tell you that very soon. Okay, now we all agree that that equations, we have a solution on that. That's the solution, right? Agree? Solution here. That's the solutions. I have C E minus AT plus, this is the constant term. A is from this A. Small a, that's from the small a. Omega is come from this omega. So this term sine times sine omega t plus the dot term times cosine omega t, and we know that that coefficient depend on the system A, small a, the forcing function amplitude, large A, and also depends on your omega, your frequencies. Okay, now the first term is C E minus AT. C cannot be determined unless we have initial conditions. Unless we know the initial conditions. If we don't know the initial condition, then C is unknown. Agree? Any problem? No? Right? So, that's we call transient solution, transient response. Now, transient response means that that solution not come from the forcing functions. And when we have a steady state response, that is the term from your forcing term, from your force. So look at, because we have two terms. Any solutions, any differential equations, any ODE like this, we have two terms. One is a transient response. But let me put it this way. If I give a force to a system, then I have two system response. One is from transient. That means before I give the force to the system, that response already exists. The second term is caused by your force term. So assume your initial condition are 0, then C will be 0. Okay. Understand? Both terms are important, not just on one term. But in control, all the control deal with steady state. We don't really deal with the transient response at all. All right, we'll tell you why. Okay. Now here I define a W parenthesis omega. Look at that carefully. And that I have W omega, that is just that's for the convenience of quantifying the response. The W, the capital W parenthesis omega equal to A divided by square root A plus then omega divided by A then parenthesis square and so on. And that we can see here. That's W omega. And then I put these two terms together, become cosine omega t minus phi. And phi is defined tangent, the arctangent omega divided by A. That's omega here, divided by A. Okay. Now, let us look at that term carefully, because this is the way we like to later on when we design a controller to your system, and this is the term, two terms. You look at the phase, we go phi. You look at the amplitude, we go W. So that cap W here, we'll explain this later, and that phi here, that's the way you quantify the response of the steady state response. So two terms, two constant. One is W, that's function of omega. One is phi, that's a function of omega 2. All right? Now, you can write a solution in all different ways. This is one way to do it, and this is a conventional way for a controller design, for a controller designer to quantify their response, how good your design is. All right? So remember this, these two terms. We always write this way. We don't write that way. We write this way. It's the same thing. Okay? And later on, the W omega, this is really the gain. We call the gain. We'll show you later. Okay. That's now That's, well, let me write it down here. Maybe I talk a little bit here. That would be good. So this is W omega. And then I have a free not phase. So that's the phase. Okay. And that's we call it again later on. Okay. That's the way we define. We'll show you why we look at that. All right. Yeah. All right. Now the transient solutions. Now we are going to talk about transient solution first. We then come back to talk about steady state. We got to understand the transient solution before you go to steady state. In other words, if you are a good designer, controller designer, you got to understand your system first. Then based on your system, you design a controller to control the system. Agree? If you don't know anything about a system, how can you design a controller? Can you do it? No? Are you sure?
Oh,
Huh?
I think it's
If you don't know anything about a system, can you design a controller for the system? Yes, you think so now.
yeah.
Are you sure? Anybody? That's a good question, right? That's a good question, really good questions. And the answer is yes and no. So first of all, you say yes, it's also right. You say no, it's also right. Well, why? Because if you don't know anything about the system, then you can design a TMD. I say TMD put to the system. It's not going to damage the system. However, it may not help the system at all too if you don't tune your TMD in the right way. Okay? But if you design a controller, which is not TMD, and if you don't know the system at all, oh, that's dangerous. I don't want to do that. Because you might, instead of dissipate the system energy, you might add energy to the system. You don't want to add energy to the system, that won't be too good, right? Agree? Like 101. You keep adding energy to the system, 101 will collapse. All right, but we will talk about that too, right? All right, so this will show you that the A, how much A the response, and how much A will give you how much is the response. And A equal to 1, that means E minus T, that's the response you have. A equal to 2, then the response is much quicker. So your system, how much your system, how much A in your system is really affect your controller design. So for this case, A equal to 2, the system will decay faster than A equal to 1. That's true, right? That's for this is only for first order system. We are not talking about second order here. The first order system, A can be negative, can be positive. Any system A, if any system A is positive, then we call A is what? We call system is what? Unstable. Well, think about that. If A is negative, then the system response will grow, right? Because if A is positive, then E minus AT, the system will decay. So it doesn't matter what kind of initial condition you get. By about 6 seconds, that transient solution, that transient response is gone. Okay? Agree? Understand? So your system A is important. System transient response will be gone in few seconds if you have a right eigenvalues. Think about that. If 101, if the earthquake come in, if I don't have anything TMD on the top of the 101, then a 101, when earthquake is gone, the 101 will decay. The vibration of 101 is supposed to decay, right? If they don't, then that design is terrible design. So I believe the 101, the system A, should be like this. I don't know. I'm just guessing. Okay. Harmonic excitation. A harmonic excitation excites to the system. We expect to have a phase angle leg. Like for example, like this. The blue line is your forcing functions. The green line is your steady state response. So your steady state response will have some angle delay. In other words, when earthquake come in to excite the 101, then they don't respond right away. They have a phase delay. All right. So you look at that. That's the phase delay. The angle, that angle phi, tell you how much the phase delay you will get. So that has a physical meaning. I'm talking about now phase phi, not phase angle. Now phase angle does have some physical meaning in it. Okay, sometimes it's phase lead, sometimes phase lag. It depends on your cosine theta is plus or maybe negative and so on. They have some phase lead or phase lag. We'll talk about that later too. Okay, this is the period is 2 pi over omega. That's the period. That's the same period for your forcing function omega, your cosine, and also that's also the period for your steady state response. In other words, you have cosine, you have cosine in, you have cosine out. When you have cosine function excite the system, you have cosine response from the system. Human being the same. When you eat something here, you out something out, right? Yeah, so you better eat good food. You got a good out. You eat a lousy food, then you got a lousy out. Right? Junk food, junk back. Agree? The same thing as any system like that. Then you have a nice, very nice cosine in there, in the system. You get a very nice, smooth cosine out. But unfortunately, earthquake won't be like that. Earthquake may have several different frequencies involved in there. So your response will be also many frequencies response add together. And any signal come in, that signal can be represented by a finite number of cosine and sine function adding together. So this is why we study only one cosine. But even that we study one cosine, that doesn't mean your excitation is only one cosine, only one frequency. No. Okay. I already give you the physical meaning of the phi. Okay, let us look at real example. Assume I have a value for that, a small a, and I have large a at 1.8 there, and I have omega, which is 10 radian per second. And then when you solve that, so we have an input that's a 8.248 cosine 10t. And then that's my input to the system. And then I have a transient response because I have A, give the A there, 4.5766. So my transient response will be 0.6 E minus 4.57661. I did not show you the initial condition yet. I think I bet initial condition is down. It's somewhere. Initial condition I will show you later. Because for that transient response, you do have to give them a transient response. You do have to give them the initial conditions. All right. Then you have a steady state. And on the right hand, the bottom corner, you have steady state response there. Then the transient plus steady state, then that's my real response is here. It's there. It's there. That's my real adding together this plus that. That's my overall response. You can see that transient is gone in about 1 second. Transient's gone. So this response is just looks like your just exact like your steady state response. That's it. The transient response will be gone in 1 second. All right. That's why, in many cases, the control only deal with the steady state response. We all assume transient response. The transient response will decay because model system, they are stable system. The transient response, they will take care of themselves. In matter of fact, you are really control design. You're not really dealing with the transient response. You're dealing with the steady state response. But now you look at that carefully. What is the differences between this response and my input? Look at that. What is the difference between this? That and that. Did you see any difference? You can see your face different, right? What else? Your amplitude is different. The amplitude is 8.4248. But the amplitude there is 0.75. Okay. And that 0.75 compared with 8.248, that means your response, your gain, you have a gain. That's come from your W transit omega. You have large input area of 8.248, but your response has only 0.75. That's good, right? You have a lot of force in there, a lot of amplitude in there, but your system only responds to small amplitude. You don't want to have, say, I have an input, my response is much larger than my output is much larger than my input. That won't be too good, right? So, you look at this. Look at that two curve, the upper curve and the lower one. The upper one and lower one, you can see the phase is different, the amplitude is different. So for any response, we look at their amplitude, we look at their phase. So this is why I have a gain, W omega there. This gain is good because that gain is small, right? You don't really gain, you lose. Right? But in control terminology, you still call gain. Okay. This one show you when your excitation, your frequency is changing. All right, and if your frequency is changing from a very small 0.1, 10 to minus 1 is 0.1, change to 10, your gain will getting smaller. In other words, if your frequency is higher, your response will be lower. This one here. The frequency higher means your amplitude, your output, steady state amplitude will be smaller. Then your phase angle also changing. Your phase angle also from 0 and change to 90 degrees. Then if you have frequency high enough, your phase stack will be like a 90 degree. So look at this curve, then you will be able to tell me what kind of frequency is better for the system. Right. It depends on your what you want. If this is the building, I also, of course, I wish all the earthquake frequencies will be in the higher side, right? Then my response, because of that frequencies, amplitude won't be large. And that's what I wish. But if not, then I can worry, right? But of course, the frequency won't be 0. But if frequency is 0, your gain is only 1. That means 1 means what? 1 is your gain is 0. Well, that's dB. Now the dB I will explain to you. That dB is different from what we are thinking about. That dB is less. If dB is log, you get log gain, log 10, and then 20 multiplied by log 10, multiplied by the gain, that's W now. All right, and 0 means gain 1. That means 1. Okay? Understand now? What I really want to do here is to explain to you the physical meaning of the W there gain, and the phase angle. Any questions? No? Okay. Think about that, huh? Again, I'm not talking about math. I'm talking about meaning. Okay, here dB is there, 20 log 10 G, and that G is W parentheses omega divided by the ATA equal to 1 divided by square root of A squared plus omega squared. A is your system A. Omega is your input omega. A, your system, you can say A is your system eigenvalue. Omega is your input frequencies. Understand? Okay? No problem? Okay. And that's the phasing. So when omega is giving increase, you know, and then that's going to get more like 90 degrees. And when that omega is more and more, then again it's getting smaller and smaller until again it equals 0. Now the dB is way below a negative value. That's what should be. If omega A equal to 0, that's 1 over square root A squared is 1 over A. That's all you got. Any problem? Okay. Now, these two chart is the chart you quantify your responses. Right? So to judge your controller design is good or bad, we can plot your gain, your phase. That's the way we judge. Okay, understand? That's the way we look at our response. That's the way we say he is a good controller design or not. Okay. So the maximum gain is 0 dB, G omega equal to 1 with the frequency omega at 0. And the phase angle changes trend at omega equal to 1. Okay. Omega equal to 1, change the trend, to change the slope from this change to another slope. Any problem about this? It doesn't look like a 1 when omega equal to 0. Am I missing something? No, A equal to 1. Because in the top there, I say A equal to 1. A equal to 1. Right? This curve, we plotted A equal to 1. And kept A equal to 1 too. Small a, assume A equal to 1, kept A equal to 1. So that means omega equal to 0, gain equal to 1. Understand? Okay. We can move. Okay. Now, to solve the same equations, then we propose another approach called complex variables. It's complex variables. And if you look at this carefully, these two equations, that and that, are they identical or not? And I have a complex number here. A, E, I, omega t. E, I, omega t. Well, you know that E, I, omega t equal to cosine omega t plus I sine omega t. All right? Agree? So that two equations are not identical. Because I add a I sine omega t to the equations. But, see, this is tricks. Can you have any I sine omega t input to the system? What does that mean? If I have I sine omega t to the system, what does that mean? What does that mean? That means nothing. It's impossible to do that way. There are no such I sine omega t input. So why I want to do that? Again, quote. This is just for my mathematical convenience. It's nothing to do with physics. So I add there just so that I can solve that differential equation much easier. That's all. After I solve it, I gotta come back to take out that imaginary part, because that doesn't have any physical meaning. Understand? Now why I want to do that? Because exponential functions, if you have exponential function to be your input, you can solve that differential equation much easier. Agree? Okay, that's what I do. But if I'm not going to solve the left-hand side equations, which is a cosine omega t, I'm going to solve the right-hand side differential equation, which is a exponential I omega t, because that's easier to solve it. I can assume my steady solution will be, I call W small wc, that C means complex approach, parenthesis T equal to capital WC, parenthesis I omega, parenthesis E I omega T, right? We know that. So you sub in there, then I will be able to solve this WC I omega T equal to A divided by A plus I omega and equal to, and so on, I omega equal to that. Then look at that. A divided by square root 1 plus parenthesis omega divided by A parenthesis square, that term is exactly the same what we got from the previous slide. Right? Except we have now right hand side we have exponential minus I or 3, and that 3 will be the tangle minus 1 omega divided by A. That's also the phase angle we got. Agree? So this is much easier for you to solve, for us to solve a differential equations. But when after we solve it, we just have to be careful that the imaginary part doesn't have any physical meaning. Make sense? So if you take course, the complex variable, anybody have already taken the complex variable class? Complex? Do you? In your engineering mathematics, do they talk about complex variable? You do, right? Complex variable, right? You do, everybody? This is the applications. So, matter of fact, complex variable doesn't have any physical meaning. The complex variable really just for the mathematical sense. There's not really a physical meaning for that. So this is why I introduced the complex variable here in the control class. All the differential equation really solved by the complex approach. Okay, I will take a 10 minutes break now.
那个关不掉
啊，
那个关不掉，
关不掉。
对，它会开。
很奇怪，设定关不掉，又抛弃。